When it comes to basic research, in fact, most research, almost always, especially in the applied fields, people are interested in the p-value or the outcome, or whatever statistical analysis they ran. And so this actually evolved from a seminar I had given at the University of Scranton on p-values, which I sort of took sections out of for here. So there I had almost all day, so definitely a lot more content. I think it's good always to start at the beginning, and especially since you may be using a p-value, but can you define it? Right? So if we ask the media, they always come down to a quote about chance. And so you'll see here in this slide, the black bold is the author's original emphasis. So in red is what I'm highlighting, sort of the summary statement from, in this case, this particular book. Essentially, that last clause is what I'm talking about. Is real and could not have arisen by chance. Look, also, the New York Times sort of has the same summary. Will probably do only the chance. You've ever seen some of the Google talks? Here's one that incorporated sort of manipulations in research and in math. And the author Charles Sabie defined it as the probability that you see this effect by chance alone. So what is actually a p-value? Because all those are wrong, right? All those definitions are wrong, which is not uncommon for the media to get stuff wrong like that, especially in a technical context. So it's a probability. And in our case, it's actually an area, not just a point, because we're actually going to talk about outcomes that are as extreme as what's seen or more extreme. It's also given that the null hypothesis is true. And importantly, the part that the media completely missed, due only to random sampling error. Right? This doesn't account for any type of systematic error. So this is the chance or the probability that those results are seen, given the null hypothesis is true, due to sampling variability. And then, a real statistician will correct me and say, well, it's actually the results are consistent with those being due to chance. But I'm an applied statistician, so I take the color. So there's really three parts to the p-value. There's the probability, which most people are probably familiar with. It's sort of an outcome that's classified as an event over the total possible. And in our case, we're talking about an area, so it's a set of events over the total possible. If the null hypothesis is true, that is, given there's no effect, there's no mean difference, there's no relationship. And due to sampling error, only sampling error. That is, when we test something, we always take an estimate relative to its standard error, which is simply the standard deviation of the sampling distribution. And the sampling distribution is one of a statistic, right? And the standard error is simply the standard deviation of the sampling distribution. So if you repeatedly drew samples from a population and calculated the statistic each time, you would find a sampling distribution. The standard deviation of that is the standard error. So what's the value for the p-value? And it's been adopted for null hypothesis testing. So again, to jump back, we'll just review null hypothesis testing real quickly. You're probably mostly familiar with it. A priori, we set up a null hypothesis and an alternative hypothesis. The null hypothesis says there's no effect or there's no relationship. The alternative hypothesis simply says the opposite, that there is one. The important things to remember are they must be mutually exclusive, so your outcome can't fall into both categories, or your results don't. And they essentially need to cover all possible outcomes. I recently learned that this table is called a confusion table by students. This is what happens when you categorize your results as either finding something as significant or true and false. And so we have, in reality, is what's in the column format, and the results of our research is in the rows. And you see there's sort of three different conclusions that can happen when you dichotomize something to being true or false, or does an effect exist or not. And that's, you can come to a correct decision, you can fail to find an effect, or you can falsely find an effect. And so for our cases here, we talk about type 1 error, which is falsely claiming an effect is present. The not as talked about type 2 error is failing to find a true effect that does exist. We also refer to these as alpha and beta. So where does the p-value come in? Well, the p-value now has been set for what will tell us whether our results are significant or not. That is, it's the cutoff that we're going to use to say whether the alternative hypothesis or the null hypothesis is met. Now, why 0.5? I have no idea, right? Nobody really has any idea. What they'll go back to is this quote from Fisher in his book, The Statistical Methods for Research Workers, where he says, it is convenient to take this point, and he's talking about 1 in 20. In the same text, a little further down, he'll also say, look, if the 1 in 20 is not strict enough, why don't we use 1 in 50 or 1 in 100? So people will tell you Fisher chose 0.5, but he didn't really choose 0.5, right? He was sort of offering, in one context, he would use 0.5. I think the bottom quote is the more important one. So we'll pick up, I was just saying that even though we're using 0.5, in the same text that people fall back on for that, he doesn't actually say 0.5. He's sort of context dependent. So now just the 30-second history. The p-values come from Fisher, whereas the null hypothesis versus alternative testing comes from a different school of thought, and that's sort of Egon Pearson, who's Carl Pearson's son. And in that case, they're not relying on a p-value specifically. What they do is they a priori pick an error rate, and you find a critical statistic that is associated with the error rate. Then you take what you observe and find that relative to the critical statistic. And then, so that the critical statistic is based off some sort of distributional assumption. And then you sort of look at repeated sampling in that case, in a well-defined population, and I'll come back to that in a minute. Pure statisticians will also tell us that these two are incompatible, which is odd because we've made some good advances using it, so there must be some utility in it. So what are sort of the problems with p-values, other than people not understanding how to define it? Well, the first thing, the p-value doesn't indicate a degree of significance. The smaller it is, that doesn't indicate that your effect was stronger. There's no such thing as marginal significance or trending towards significance. How do you know it's not trending away from significance? It's the real question. They're not probabilities. They're not probabilities about alternative hypotheses. Right? It's given the null hypothesis is true, is in the definition. And we'll talk about how there's sort of a Bayesian way to get around that. Also, your p-value that's observed does not equal your observed alpha rate. Right? If you observe value of 0.034, that doesn't mean you have a 3.4% chance of committing a type 1 error. Right? We should know that intrinsically because that's a rate, which you don't get from one observation. Right? You would need repeated measurements to find what that rate would be. And that actually goes back to sort of the null and alternative hypothesis testing, where alpha is actually based on repeated random sampling from a well-defined population. Sort of the long-run average. Now, what happens when you combine 3 and 4? Well, you get the fallacy of the transpose conditional. The p-value is the probability of your data given the null hypothesis is true. It is not the probability of the null hypothesis being true given your data. There's a subtle difference there, and I'll talk about it more when we get to the Bayesian part. What are some other problems with the p-value? Well, the two sort of common ones are publication bias and, in my mind, the 0.5 target. That is, anything less than 0.5 is not relevant or not important, and anything underneath it is. So we just think about what we've done. We've taken some sort of results and dichotomized it into whether something's significant or not, something important or not. Even our language to describe that, right? It's significant or it's not significant is biasing. What about publication bias? Well, if we think about what studies and what results are going to be published, you sort of intrinsically know that things that are significant are going to be published and ones that are not are not. Now, is that actually the case? We'll talk about that in a minute. But that leads to what's called the file drawer problem. Whereas people who take non-significant results and just put them in the back of the drawer and they move on to the next experiment to find significance. And of course, the worst case of the circular file problem, right, where you don't even acknowledge that you ran the test that failed to find significance. So now we come to the conclusion, does publication bias exist? Is it true? Well, in 2009, there was a meta-analysis of meta-analyses, right? So, meta-analysis. So these guys looked at 5 different meta-analyses covering 750 articles that are exclusively clinical trials. And what did they find? Well, significant findings were 4 times more likely to be published. Now, we're not doing everything wrong, right? I think something that was just as important is the bullet underneath. The sex of the first author, investigator rank, size of the trial, and source of the funding had no effect. So we're doing some things correct. A different group looked at all cohort studies in 2008. And they found that, so for clinical trials, it was 4 times more likely. In a cohort study, it's 3 times more likely to get published, if you're significant or not. The real problem with trying to fix these is it requires meta-analysis or meta-analytic thinking. And so what is meta-analysis? And so here's the 1-slide, 30-second definition of what meta-analysis is. If we take a whole bunch of different studies and their findings and combine them, we should come up with a less biased, more accurate picture of what's going on. So in this case, if we take each of these dots with the error bars in them as a study, you'll find that each study comes up with a point estimate and some amount of variability next to that, so some standard error, standard deviation. And you'll see here that there's 14 studies plotted, and individually 6 have failed to find an effect. That is, their range encompassed the 0 point. But if we look across all 14, you can see there's actually sort of a robust effect down below, and that's indicated by the pooled estimate. So what we're doing is we're combining results that might not be as sensitive across a whole bunch of studies to try and get a more accurate picture of what's going on. So there's sort of roughly 2 ways to try and find publication bias and fix it. The first is sort of using a funnel plot, and the second is trying to estimate the number of studies that are in the file drawer. So a funnel plot is simply a scatter plot that looks at some variation of study size by effect. And if you do it and there's no bias in the literature, you'll come up with what is pictured here. There's no XY relationship in that it's not linear or quadratic. And what we see is as study size gets larger, we get closer to what the true effect should be found. And you'll see that as the study size is smaller, we expect more variable answers, right? Because it's not going to represent the population as well. And so you'll see that the estimates are sort of all over the size. Where we can find if there's publication bias is if small studies are not being published, that the effect was small. So you'll see there's a little hole here, right? That is, we're not finding significance in small samples, so people are not publishing literature to fill that hole. So what can you do? Well, you can actually sort of try and figure out what's missing and impute sort of an estimate of what would be expected. So we can create data sets or findings and combine those with what's already there, and then look at the effect. There's some problems with this. There's no universal method on how to actually do the imputation. Also, by including something you're randomly creating, you could be potentially including more bias than you're getting rid of. And here's the real thing. Does it work? No. So they asked clinical researchers to look at funnel plots, and they were able to accurately identify the hole 53% of the time. So not so much. Alternatively speaking, if you do find a hole, there's actually some evidence that the trim method actually works. So inserting the imputed data works. Sort of of the other way to go about finding publication bias is you try and estimate the number of studies that are not published that would wash the effect out. So you find all the studies that have the effect, and you look at the strength of that effect, and you try and estimate the number of studies that you would need to be unpublished that had not significant findings that would eliminate that. And this is called the fail-safe file drawer method. First problem is there's no set way on how to calculate that number. Also, you're incorrectly assuming that all the things in the file drawer have a null finding, right? Or you can attempt to say some of those unpublished have an effect in the opposite direction, but you really have no way of knowing how strong the opposite direction would be. So there's really no good solution. I talked in the beginning for this little section, I mentioned that I want to talk about sort of two aspects. The other one is the consequence of this target, of finding significance and not finding significance. It really easily lends itself to manipulation. Right? One more comparison. I might find 05 here. So, a couple guys looked at 3 psych journals over the course, I think it's 13 months, and they wanted to know what the relationship was of the p-values that were reported. And they found that values just below 05 were off trend. You'll see here that the 4 charts are just different bin sizes for the actual p-values. But you'll see here the dotted line represents 05, and you'll see there's a jump right there, which indicates that there's a lot of papers finding just significant results that are off trend. Sort of following that work, these guys are wondering if there was an effect that over time that this is getting worse. So they looked at 2 journals, and they found that it is getting worse over time. And you'll see here, now there's 2 bin sizes, are the top and bottom, and the 2 journals they looked at are now left and right. Now they concluded that there was an effect of time here, and I'm not so sure. It looks more like an interaction, where in the one journal there's a serious effect of time, and in the other journal it looks like there's not really much of an effect of time. Although there's still bias in both groups. And that was 65 was the earlier year, and 05 was the later year. So here's the difference that they found in one of the 2 groups and not the other. Then you get the question of, is this worse in the soft sciences or the behavioral sciences? And so an author did an examination of all sort of the results found by these different fields and concluded that as you get more behavioral and applied, there's a tendency to have greater bias. Although his effect is not really as strong as it looks. If we look down the worst fields, he combined psychology and psychiatry, which are 2 very different fields if you're in them. Maybe if you combine clinical psychology and psychiatry, that might make sense. But also look at the second worst offender was material sciences. Right? So there is some sort of a trend here, but I don't think it's nearly as strong as the soft sciences are way worse than the hard sciences. So how might we be finding these values that are just significant, that are out of whack? And I want to talk about 2 sort of instances that I think lead to it that I've often seen, and so that's anecdotal, and I apologize for that, but it's what I'm going to talk to you about today. So the first is type 1 error inflation through multiple comparisons. First of all, this is not a p-value problem, right? This is a research practice. This is where you continually test your data until you find something that was significant. We need to acknowledge that multiple comparisons are not always wrong, right? A lot of the general linear methods, the generalized linear methods, when comparing means, need to employ these. As well as when you have big, maybe structural equation models, where you're testing lots of different individual parameters on top of model fit, right? There's no way sort of to get around those multiple comparisons. But if you're doing that, you should at least tell people or adjust for those post hoc comparisons. So for example, if we're going to make 10 comparisons and our alpha a priori is 0.5, in this case, your actual type 1 error rate is 0.4. So there's a 40% chance of you falsely finding an effect. There's the formula calculated. And somebody decided to actually see if that was true and ran a simulation study and found that it was pretty close. He used 5 comparisons at 0.05, and he came up with 0.21. The formula's estimate would be 0.23. So here's an example of a paper that I'm going to hit a couple times in this talk. Marital satisfaction and breakups differ across online and offline meeting venues. I stopped counting when I got to the 74th significance test, and there were 3 more appendices left. I only counted the first 2. Of course they're going to find significance, right? Now the other big one that I see is the violation of independence. It's probably the one universal assumption that every statistical method has. Whether it's independence of subjects, independence of measurement occasions, independence of conditional independence, or disturbances, or at the highest level of clustering, it's somewhere there. So what is not counting for independence of life? Well, that's like doing a between analysis on within designs, or treating repeated measures as 2 different groups. Failing to account for repeatedly using measures from the same people, or ignoring nesting or clustering effects. So, for example, in the marital satisfaction survey, they took ratings of all the different relationships and how they liked it or enjoyed it, and they failed to account for the fact that people from their same relationship should presumably be rating it similarly. Right? Those are not independent relationships. I almost always recommend trying to use some sort of multi-level modeling to adjust for this lack of independence. These authors looked at in neuroscience and found that the inflation of type 1 error can go from 0.5 to 0.8. And so this graph is a little dense, so let me start explaining some of the things on it. The y-axis is proportion. It's both the proportion of type 1 error rate, which occurs with the 3 lines, but you'll see there's a ghosted histogram. And they actually went through the literature and counted how many times a study was published with, and then this is on the x-axis, the clustering effect. That is how many observations were in each of those clusters. And so you can see that in neuroscience, at least, the clustering analysis or multi-level modeling or hierarchical linear modeling should be used pretty often, and it was not. Now let's talk about the 3 lines. If you have a clustering effect, what does it do to your type 1 error rate? Well, if you have one as small, or an ICC as small as 0.1, you can see how quickly it inflates your type 1 error based on how many observations you would have in the cluster. Especially when you get up to an ICC of 0.5. Right? And this is not accounting for that nesting or the cluster. Whereas regardless of the ICC strength, if you use the multi-level modeling, you'll control that type 1 error. So what can we do about this, right? So I'm going to go through some of the suggestions, and most of the time they're shortcomings. So P-rep. This came out of Psychology, American APS, Psychological Science, I think it was called. That might have been before it changed its name. So here's what he suggested. We don't report p-values, we report p-rep values. I don't know how this is going to fix anything. If we look at the equation, right, there's no new information from the p-values there. It's a simple function of p. Turns out when he did the actual math, his p-rep, which supposedly gave a prediction of the probability of replicating that effect, it didn't work. On top of that, even if it had worked, we have a logical sort of rational argument problem. That's really the p-rep of replicating those findings for that sample in that setting, right? And the whole idea of replication is we want to use different populations in different settings to get a more robust effect. And it also turned out that the journal that he published in started requiring it in the journal that in the actual issue that he published it in, and he was on the journal board. That's what happened. Oh. People always talk about how confidence intervals can answer the p-value problem. So what is a confidence interval? Well, you get your point estimate, right? And it's the amount of variability inherent in the data around that estimate that you're not sure because of sampling error. And so in this case, it's simply the point estimate plus the critical value times some estimate of variability, which is the standard error. People always interpret the confidence interval wrong. It's really repeated sampling is what should be added. So 95%, if you're using 95% of the time, we run this analysis and get this interval, it will contain the true estimate. It's not, there's a 95% probability the true estimate is in this interval. And so here's sort of a demonstration of what they are. If I repeatedly sample, right, I find that these samples contain the true parameter, and every now and then I'll find that it does not. They are a more precise way of giving you the point estimate and the variability. The critical value is typically chosen based on alpha. That aligns. The problem is it gives you the same exact information as a p-value. It will never differ. So I don't know why providing confidence intervals are going to be the solution to giving p-values. Right? It's not really a problem. Not a solution either. Bayesian methods do offer some ways to get around this. And you'll recall all the way back at the beginning I talked about how the probability of your data given a null hypothesis true is different than the probability of the null hypothesis being true given your data. Well, there's a way to transform one into the other, and that's using Bayes' theorem, which is simply this. What you're essentially doing is you're taking some measure or some idea of what's the possibility that this is true. And that's your factor of plausibility. It's called a prior in Bayesian. And so you're going to multiply your results by this prior. So going into it, you sort of need to think about whether it's likely to be true or not. The other, I should mention, the bottom part of the equation is just sort of a normalizing constant. That's not really ever talked about in the applied literature. So here's essentially what we're doing. We're taking our p-value, we're taking some estimate of plausibility, applying Bayes' theorem, and we're getting what the p-value is that you want, right? And that's the probability of the null hypothesis given the data. And there's a number of ways to do this in Bayesian. I'm not a Bayesian, so I apologize if I get some of these minor technical points wrong. The first is to use a Bayes factor, which is actually analogous to a significance testing framework. It is good for comparing competing models. They are more robust than p-values. The problem is you come up with the same type of idea of where you're dichotomizing into something significant or not. And so you bring back into the conversation type 1 and type 2 errors, although they're not based on p-values now. It's also, they can give you lots of variability in complex models. Another one is use the credibility interval, which is essentially making the argument of the confidence interval that everybody does wrong. This will actually give you the interval that has a 95% chance of containing the true estimate. It's very hard in complex models, and you often have to do a sensitivity analysis, which means you have to actually apply multiple priors to see what those impacts actually have on the outcomes. There's the empirical Bayes method, which sort of combines the two. The problem is you're calculating your prior based on your observed data, so your prior is biased by the data that you're going to use to test it. And then the last one, you can sort of use a likelihood ratio or a full Bayesian analysis, which can help eliminate some of the uncertainty. Problem is you can really only look at a few nuisance parameters. It's really difficult in complex designs. In the end, often the likelihood ratio is actually equivalent to the p-value. And of course, if you don't have a model to start with, right, you have no idea what sort of prior to choose. I've also not seen anything in the literature on how to do multiple comparisons through a Bayesian framework. I'm just not familiar with the literature. There might be one out there. So I don't know how you would do a lot of post hoc testing through a Bayesian framework. What if your research is totally novel? How do you choose a prior? I guess you choose multiple priors and try and test, but think about the work that involves, right? Also, Bayesian typically involves a lot of more complicated statistics, so you need to have a stronger knowledge of statistics if you're going to use it. There's also this interesting study that was done by a Bayesian statistician. Found that when there's a strong prior, your results were biased towards that prior, which makes sense. But then he wanted to look at that impact in the real world. So he presented this scenario, or one of two scenarios, to people. The first is he had a model that could predict the next 6 instances perfectly correct, or he had a model that accounted for the previous 6 instances perfectly correct. And then after reading this article, they had to rate which they thought was stronger evidence. And by far, people said if you predict the next 6, your model is much better than if you had just previously predicted the ones that happened. So we think about this in the Bayesian framework, right? We're predicting ahead of time what we think is going to happen. So if we think it's going to happen and we find it's going to happen, we've not only biased ourselves, but our now thinking is that's probably more likely to be true. So what are, some recommendations. Give you time to read the cartoon. So the first one is avoid the shotgun studies, right? I have actually been asked to compare pre-post for a sample size of 10, for sample size of 15 with 10 different outcomes. I mean, what's the probability that I'm not going to find something significant? If you're going to data mine or data dredge or p-hack or whatever you're going to call it, right, you should at least disclose that fact in the paper. We tested all 10 of these outcomes, and one of them came out significant. If you're going to use many predictors and you don't have a strong a priori hypothesis, you can use actually what we talked about in one of the earlier seminars, a penalty function, or you can use the automated procedures to select the strongest predictors. That's sort of the stepwise, the backwards, and the forwards regression. If you have large numbers of covariates and dependent variables, right, you should switch probably to a multivariate framework. If it's confirmatory, you should use SEM. If it's exploratory, you can try and reduce the variable load through PCA or calculating a risk score. We had also briefly talked about that in one of the seminars. So what's really the problem with p-values? Is they're sample size dependent. Because what we're doing in the p-value is comparing what we got relative to sampling error. So what we really need is an indication of how strong the effect is, which is the effect size. And so effect sizes and p-values complement each other. One tells you if it's due to chance, and the other tells you how actual strong the effect is. And there's some quotes backing me up from people that are more famous. It's also been called the practical effect. Sometimes it's used interchangeably with the clinical effect, although that can be slightly different. But here's some common effect sizes for literature. So if you're comparing two means, you should use Cohen's D. If your comparison among means, you should use partial eta squared or the Cohen's F or F squared. Or you have the R squared, adjusted R squared, and the pseudo R squared for regression models. The odds ratio for linearized models. Then you can actually look at model fit, which is the AIC, BIC. Those are sort of the generic ones. In more advanced, like structural equation modelings, they have the goodness of fit and the RMSEA and different types of fit indices. Also in HLM, you can look at the ICC. So in the marital satisfaction survey that I'm going to hit again, they found that people who met their spouses online were happier than those who met in person, based on 17,600 responses. And this is the difference they found, 5.48 to 5.64 on a 7-point scale. And that was their main finding of their article, was people who met online were happier in their relationship than those who met in person. Now, one of the nice things about effect size is you can actually adapt it for further use. One example is the reliable change index. And what we're doing now is we're taking into account the inherent unreliability of the measurement. So we're going to simply multiply the standard error measurement. Then you can actually adapt that to also take into account some sort of chance, and we get what people call the minimum detectable change or the minimum clinically important difference, which is often reported in the health literature, right? You need to be a minimal clinical difference of this. And it's actually based on an effect size. Another solution is to bootstrap your results. This really helps when you fail to meet distributional assumptions in models. It has the nice effect of the confidence interval after the fact that you get the bootstrap confidence interval can be treated like the credibility index in the Bayesian, or the incorrect way to talk about a confidence interval. What you do is you treat your data, your observed data, as if it were a population. You repeatedly draw sample sizes of n from it with replacement, so a case could be selected multiple times. You calculate the parameter of interest for each one of those samples, and you actually get an empirical sampling distribution. And in that, you can get the 95% confidence interval of that, and you can sort of have an estimate of where the true effect lies. If that confidence interval covers 0, or the value you're testing against it, you would say it's not significant. Sort of the problem with bootstrapping, I guess, in days of old, was it was very computationally intensive for computers, which is funny when you read the literature up to like 97, people say it takes a long time, and then suddenly people stop complaining about computer usage. Another problem is, oftentimes, if you're looking at a parameter of interest, you have to transform your data such that the null hypothesis is true. This is done sort of in the Wallenstein bootstrap for SEM as an example. There are two inherent weaknesses. The first one is your sample that you take must be exactly representative of the population you're generalizing to. So there's actually a huge weakness in that if your sample isn't truly representative. And the not as important but more technical flaw could be that the relationship between the bootstrap and the normal sample has to be able to be replicated. Which brings me to replication, right? The best way of showing whether an effect's true. Right, and so this is the gold standard, and everybody talks about it. The advantage of replication, especially when other people are doing it, you're not replicating your own results, is you're getting a different population in a different setting done by somebody else. And if you are able to show that this effect replicates, each experiment itself could be internally highly valid, but externally not so much. But if you combine all of that across very different settings, right, you actually get a more robust external validity or generalizability out of your findings. Now, what about replication in the literature? Are people actually doing this? Well, these guys tried to look to see if it worked. So in 2013, they found that if an effect was replicated, it was more likely to be true, which sort of makes sense. If you're sort of from the sensitivity specificity framework and you're used to positive predictive values, you can use the sort of formula for that, and you can find that replicating studies increases the probability of finding that effect in the next sort of time you're going to run the experiment. And here's a little example of with 10% chance of being true and a power of 0.8. When one study finds it, another study is likely at 20% of the time. But if 2 have found it, it increases to 54%. And if 3 have found it, it's 90% going to be replicated in the future. Unfortunately, right, that publications are hardly ever replication studies. Right? It's just not valued by the journals. So one of the things that really should change is the publisher's influence. Right? And specifically, they can start simple, right? Require everybody to report all descriptive statistics. It is often very frustrating to conduct a power analysis and people provide you studies and it doesn't have the N, or it doesn't have any estimate of variability, which is annoying. But on top of that, how are people actually making sense of these articles without some of those basic information? And so I would posit that on top of the p-value, the N, some measure of variability, that you should also supply the effect size. You can force authors to maintain their data, right? And this will help with other people trying to investigate whether you have fraud or not. Another thought was that you make your data open access after so much time after the first publication comes out. Obviously, there's flaws with that, if you haven't gotten around to looking at everything in the data yet, somebody could scoop you, even though it's your data. There's also potential HIPAA violations and stuff like that. A nice one would be to value replication and generalization research. I don't know how you're going to talk people into that after all these years. You can try and certify that authors meet some minimum ethical standard. I don't know how much that will impact the people who are unethical anyway. One nice thing that I saw that some journals are now having is a statistician be the reviewer. So if there's any questions, not necessarily about the article, they'll just send the stats section to the reviewer. The conflicts of interest should also be made more clear than a paragraph all the way at the end underneath the references before the appendix. So if we go back to the marital satisfaction survey, we'll find that the author, or of the 5 authors, one is a scientific advisor for eHarmony. The second is his wife. The third was the director of the eHarmony lab. A nice thing would be to pre-register your analysis, and that is, so you state ahead of time, this is what I'm going to do. It can help with the multiple comparison problems. The bad news is this has been talked about since '85. Really hasn't been done yet. In '07, the FDA required it for some clinical trials. The big journals in '04 sort of went to this. Does it work? Yes and no. If you're required to disclose it, it works well. If it's something that's optional, it does not work all that well. For instance, only 66% of the time you can find the outcome. So it's not all that useful. These authors actually randomly sampled 10% of those that didn't report and followed up individually with the authors. And they found out that less than half of them were published. And there's actually an industry difference. So 40% of non-industry and 56% of government published, so there's a little difference there. There's a recent one that just came out, I guess it's like a month ago now, or 2 months ago. They looked at every study that was funded by this test, which is sort of a large sample survey method to get a very representative population with a high return rate. It's sort of a framework that's set up. They found out that 48% of the studies received funding or published, pretty small, but that 65% of the null findings weren't even written up. Right? It's not that they weren't published; they weren't even attempted at getting published. There's also this idea of publishing all results. Of course, competing studies found out, right, whether this works or not. One study says it does, one study says it doesn't. So I don't know if that's actually validity there. And in closing, I sort of want to go back to what Fisher said, right? The p-value itself isn't the problem, it's how researchers are using it. And I think if you supplement it with an effect size, you'll be getting off on the right foot. That's it.
So thanks, Brian. It was really wonderful. I learned a whole lot. So comments. I could go on all day.
Sure.
I'm going to try not to. So first comment is more positive about I think that about clinical trials with Gov than you are. I think that this has been a major advance because
I should mention that I wasn't around before it, so okay. I don't know what it was like before that.
So yeah, I was around way before it, unfortunately. And I hope to be around way after it. But we'll see what the posterior probability that is. So what we're really concerned about is not people who are often doing their own thing and not publishing it. It would be best to know so others don't go down a rabbit hole trying to do experiments that aren't worthwhile. But what we're really concerned about from a societal point of view is that therapies pass muster with the FDA where it's really not done properly. And so you really have a problem that a pharmaceutical company could mount multiple trials of the new drug versus the standard, and only publish one that's positive. And you wonder, did they really do something like that? And the answer is, they really did stuff like that. So they really did the bad societal stuff, and they can't do that anymore. They must register it in advance. And if they don't register in advance, the FDA won't accept it. And the FDA is going around trolling clinicaltrials.gov. They know what the pharmaceuticals are. So it's resulted in a great deal more transparency, but it's not perfect. So that would be a little more to the point about multiple comparisons. One of my favorites is a study by Peter Slight and colleagues from Oxford, follow-up to the ISIS trial, which showed the advantage of streptokinase and aspirin in acute myocardial infarction. We got consistent results in every subgroup by astrological sign except for Libra and Capricorn. So obviously their goal was to show you the problem multiple comparisons. Let me ask you a question about publication bias, because we know that there are more positive studies published than negative studies. But so we put it in Bayesian framework. Do we know if you have a negative study versus having a positive, or are you more likely to publish? And how would we know along the lines of the funnel plot? Because
you don't know, right? Know. I don't have an answer. I don't think, I'm guessing it would be field dependent, right? If you look back, some of those fields, positive findings are like 50% of the time. Whereas if you get down to psychiatry, it was 90-something% of the time. So I would think those would have the larger issue. So I don't know where cardiac stuff falls. If that's what you're worried about.
I'm worried about
anything.
I'm worried.
Sure. Yeah, I agree with Bill. I think I would not be as pessimistic as you are regarding also the requirements of the journals, because now most of the journals only require the writers the authors to adhere to the to some guidelines regarding publishing, regarding the description of all the characteristics of the population, the famous table 1 and these kind of things. And either for clinical trial or for epidemiological studies, you have to tell them to show that you adhere to these guidelines. I think there is a trend towards doing better things.
Hi there, Ryan and audience. Can you hear me?
Yes.
Okay, thanks. I'm J.P. Lawrence, so I'm from psychology here on main campus, and I just had a question about the effect sizes. First of all, I enjoyed the talk. I thought it was really right on, and I had a question though about effect sizes for things like effects in multi-level modeling. I mean, I know you put up the ICC as an example of an effect size, but I think that really just focuses on the within between variance. But in terms of actually like getting something like a D or an R in that context, I find that really challenging. And so I think sometimes there are some statistical methods that it's just hard to come up with an effect size that actually captures what's going on and can be compared from study to study. But I didn't know if you had any thoughts about that.
Yeah, the only ones I'm familiar with are sort of the pseudo R-squared ones, which you can't actually look at interaction effects with, because it just looks at the reduction in variability of the residuals around the effects, whether including it or not including it in the model.
Right. Sometimes those R-squares can become negative in multi-level modeling. That's what's funny.
Yeah. You should hurry up and create one.
Thanks for your time. I appreciate it.
Sure.